Okay, good morning. Okay, so today we will look at more examples on solving recurrence using generating function. And then, so we are going to look at an example which is related to string matching. So suppose that we have a string, a bit string, like this, 1101010 blah blah blah. And assume that we are going to read this string from left to right. So we are going to scan this, scanning. And use this method to detect a certain pattern, whether it occurs or not, and if so, how many times. So for instance, let's say we have a target pattern, 010. So this is our target pattern. So we are going to scan 010, compare with every position here, and so on and so forth, until we are going to find the first match. So here, we will see that 010 appears at this location. Is that okay? And moreover, let's say we are interested in finding non-overlapping matches. So once we have 010 matching here, we will chop off everything before and continue matching here. Is that okay? So in that case, if you look at this string, we will say that there are going to be two occurrences of 010 using this process. So we have detected two non-overlapping 010. Okay. Now this is, and then we will call this position. This is the position where 010 first occurs. And then this is not just first occur. Okay. And how about this one? This is the position that 010 second occurs. It occurs the second time. Or in general, we just say that this is the position that 010 occurs. Is that okay? But how about this one? This one, no. We don't say that 010 occurs at this location. Is that okay? Using our process. Okay? Now, let us try to answer the following question. Okay, so the first question we want to ask is, so how many n-bit string that 010 occurs at position n. So this is the first question. And then the other one is similar. Again, how many n-bit strings such that 010 first occurs at position n. Okay, and actually we are also interested in how many n-bit string that 010 occurs at any position. Okay, okay. So let's try to answer this question and see how we can do. Okay, so let's establish the recurrence for this problem. So suppose that we are going to use, let me call it Bn, okay. Number of n-bit string that 010 occurs at position n. So we let Bn to be this one. So you have an n-bit string, length n. So first of all, we will know that B1 and B2 should be equal to 0. Am I correct? Because the length is not enough. For B0, let's decide it later. And so that means that we have a string that is very long, and then we have 0, 1, 0 here, right? So So is it equal to 2 to the power n minus 3? No. Yeah. So what? So these three positions you need to have 0, 1, 0, right? For this to occur. And so we can fill all the other things by anything like 1, 1, or 0, 0, 0, right? So there are 2 to the power n minus 3 choice for this to occur. But this is not true. This is 2 to the power n minus 3 is not the number of strings with 0, 1, 0 occurring at the nth position. The reason, you may have 0, 1, 0 here, and then 0, 1, 0, and then this is the position where 0, 1, 0 occurring. Is that okay? So what should we do? So it is not 2 to the power n minus 3. We should minus something. Minus what? Minus what? We should take away those strings of length n minus 2 such that 0, 1, 0 occurs at the position. Does that make sense? Okay, that's easy. We should take away b n minus 2. Is that okay? Good. That's all we need. Okay? So we have now a recurrence. We have initial condition b1, b2 is equal to 0, we know, right? And then because of b1, b2, there is some problem. What is b3? So what is b3? b3 is actually equal to 1. Excellent. Okay. So at this point, let us set up what is b0. So we hope that b0 should satisfy. So we want to have what? We want to have b0. Okay, b0 is like b2 plus is equal to let's say n is equal to 3. 3 minus 1, 3 minus we don't need to have b0, right? Let me check. What should we set for b0? b3 is 1. Sorry, this is not bn minus. This is bn minus 2. That's true. Let me see. So let's fix b0 later. Okay. So b0 is not important at this point. Okay. So how can we solve this one? So we will know what? We will know. So the first line that we can have is b3 is equal to 2 to b, or let me rearrange these terms. Okay, so we should have something like what? We should have something like b3 plus b. Sorry. The other part is mechanical, so I want to find a good way to write it down. So anyway, yeah. So let's try. So let's say b3 is equal to 2 to the power 3 minus 3 minus b1. Is that okay? So we will have b4 is equal to 2 to the power 4 minus 3 minus b2. Am I correct? Okay, we will have many things to write. So we will have bn is equal to 2 to the power n minus 3 minus b n minus 2. Is that okay? So we are going to add everything together. And before that, let us multiply this. Let's say this with x to the power cube, x to the power 4, x to the power n. So we have x to the power 3, x to the power 4, x to the power n, and x to the power n here. Is that okay? So what do we have? So what do we have? So we don't have B0. We don't have B0 at this point. So let's set B0 to something that is for our convenient purpose. Let's set it to 1. Okay, because usually a generating function will have the constant term 1. So let's set it to 1. Okay, you can set it to any number, but let's set it to 1. Then what do we have? What do we have? If we sum everything together, this left-hand side, so this left-hand side is equal to what? This left-hand side is equal to bx minus, so the left-hand side is going to be equal to bx minus b2x squared minus b1x minus b0, right? But the b2 and b1 are 1 already, so it is exactly bx minus 1. Is that okay? So this is the left-hand side. And how about this one? This one, tedious. So let's write it in this form. So we are going to sum what? Summation of 2 to the power k minus 3 x to the power k, where k is starting from 3 up to infinity. Is that okay? Is that okay? And then minus, how about this one? This one is exactly x squared minus bx minus 1. Am I correct? Does that make sense? Is it correct? Because we take out x squared, then we will have b1x, b2x squared, bn minus 2, x to the power n minus 2. So after taking x squared out, it is like bx minus b0. Is that okay? Okay. So good. So what? So we will have 1 plus x squared bx minus 1 is equal to this one. So what is this? This is like, if I take out x to the power 3, then the first term will then be 1, and then the next term will be 2x, and then the next term will be 2 squared x squared, and so on and so forth. Is that okay? So if I take out x to the power cube, so this will be equal to 1 plus 2x plus 2x squared. Okay? So this is equal to x cubed divided by 1 minus 2x. Is that okay? Is that okay? So what do we have? So this implies that b of x is equal to x cubed divided by 1 minus 2x, 1 plus x squared plus 1. Okay? Is that okay? Okay? Yeah, maybe wrong, but looks correct. Okay? So the key point here is that once you have a problem, as soon as you can derive the recurrence relation, then you can be very happy. It is like you use generating function and then simplifying terms, and then you will be able to get the generating function of the terms that you want. Okay? So this is the first example. Okay? How about the next one? So how many strings of n bits such that 0, 1, 0 first occurs at position n? Okay. So we can analyze this from scratch, but there is a better way. Let's take a look. Okay. So here you have a string such that, let's say 0, 1, 0 first occurs at this location. Let's say this location position k. Let's say this is position k. Okay? then what should we do? Then let me see. So we want to relate. So we want to relate this an. So let's say an denotes what? The number of n-bit string with 0, 1, 0 first occurs at position n. Okay. So so this is what we want. We want that 0, 1, 0 first occurs at position n. We want to relate an. So it's an. Are there any relationship between an and the terms a1, a2, up to an minus 1, and also b1, b2, also b0, let's say, up to bn minus 1? So if we can establish a certain kind of relationship between this a and b, then because we now know b, we can use b to help us to solve this a. So if this is what? So let me write down what can we derive so far. So first of all, let's examine Bn again. Bn just requires 0, 1, 0 occur at the last position n. So Bn just look at whether this is 0, 1, 0 here. Is that okay? So one thing to have 0, 1, 0 occurring here is so how do we get such a string? So you may have 0, 1, 0 occurring at this location at the first time. So this is one possible case. Is that okay? So it will include an. So an will be the case where 0, 1, 0 occurs here at the first time. Or what? Or you may have 0, 1, 0 occurring at this location at the first time, but then you see 0, 1, 0 again. Does that make sense? Okay. So this should also be handled. So we will also have an minus 3 to be counted. Is that okay? And you can also have, so if this is, so what we are counting, okay, either this 0, 1, 0 is the first occurrence or it is not the first occurrence. So if it is not the first occurrence, then where is the first occurrence? So the first occurrence may be at this location, 0, 1, 0, okay, and then we have 0, 1, 0 appending at the end. Or we may have the first occurrence one position further, and then you can have anything here, and then you attach 0, 1, 0. Is that okay? So you will have what? You will have an minus 4. This is the case where 0, 1, 0 first occur at this location, and then you can have anything here. Can we? Yeah, we can have anything here. That should be okay, right? We can have anything here. So there are two choices here. Does that make sense? Is that okay? Yeah, I hope I'm not making. Well, you may also think of this as, right? So this 2 is correct. But you may also think of this 2 as, I will have 0, 1, 0 first occur at this location. This is first. But then, I want to have 0, 1, 0 occurring at this location. Is that okay? So the 2 that I write here, although it represents that I can have a 0 or a 1 here, but actually, what I want is that if I look at all the strings that is after that, I hope 0, 1, 0 appears at the end. So we can actually write this as B4. Is that okay? So this is perhaps the hardest part. Is that okay? And then there is another case. So I may have 0, 1, 0 first occur at this location, an minus 5. And then what I want is that I want in the last 5 position, I can get 0, 1, 0 appearing here. So this time, although I have question mark here, we need to be careful. This is not 4 anymore. So you cannot write down 0, 0, 0, 1, 1, 0, 1, 1. Not all the cases are correct. Because if it is like 0, 1, then you have 0, 1, 0, 1, 0. Then you don't see an occurrence here. So that's why it is safe to use B5 instead of, so we don't need to count because we now have B5 already. Is that okay? So we continue the process. So in the extreme case, that we will have is 0, 1, or we will have 0, 1, 0 appearing at the beginning. There are 3 positions here. And so there are going to be n minus 3 positions here. So you will have, in the last case, A3 multiplied with Bn minus 3. Is that okay? Is that okay? Actually, B3 is 1, so we can write down B3 here. Okay? And then luckily, B0, we set it to 1. Okay, so we are so clever. We set B0 to be a useful term, so that this is not just an, this is also an B0. Is that okay? And luckily, B1 and B2 are 0, right? So you can actually add 2 more terms here without any error. So we can actually add an minus 1 B1 and an minus 2 B2 here without any problem because we have B0 is equal to 1, B1 is equal to 0, and B2 is equal to 0 when we compute our B at the beginning. Okay? So this B is exactly the B that we have computed with all the boundary conditions set to our convenience. Okay? And then we now have a recurrence. And this recurrence looks like what? This is a convolution. Good.